Okay, welcome to Lab 0. Let's go through it and help you get started. So hopefully you see the write-up very close to where you are seeing this video. Do click on that too. That's important that you read the write-up. I'll walk you through it today. I also do want to say that this is like the 0th lab in the class, so it's definitely the easiest. You want to save, like I want you to do all the labs, of course, but like if things happen and a lab gets dropped, don't make it this one, okay? This one's an easier one. So let's go to the write-up and go through it. So here it is, Lab 0. It's got 3 parts to it. So you're going to be essentially writing 3 different programs about different things. But the very first step is to get the starter code. I've made a bunch of just code for you to fill in, and that'll be a piece of what you turn in. And to get that code, you need to be logged in on the class server under your account. And I made this cute little gimme command. So let's log in on the class server. So I'm going to SSH into my account. Remember, your account is, your username is your last name underscore your student ID at, if you're doing it this way, it's an @ server.lawtonsclass.com, but do check the SSH client page on our canvas to get logged in and to remember all this stuff. So the very first time you log in, your password is the same as your username, even though you may have changed your password on the class website. This is not linked, though the account name is the same, though the username is the same. So you'll type your username one more time if you haven't done this yet. And then the first time you log in, it'll force you to change your password. And I can't talk and type, so give me another try. It'll force you to change your password when you log in for the first time. But eventually you'll get to the cow, and that's where you want to be. All right. So I have an empty home folder right now, just like you do. So let me make a new folder for where I want to do my work, because the very first step before I even run this is to get where I want to do my work. So I'll say, I'll make a new folder called like labs or something. Like maybe I want to do all my work inside of a labs folder inside of my home folder. So I'll go inside of that. Again, it's empty. And now if I say the magic gimme command, gimme name of the lab, lab 00 at CSCI26, hit enter, wherever I was, it will create a new folder called lab 00, and I can cd inside of that. Alright, so here I am. I got a bunch of files, and I can get started and look at them, compile them, all that fun stuff. So the very first step to this lab is to write a hello world program. Alright, so you're going to write just a program that prints hello world to the screen. Your file has to be called hello.cpp, so I've made that for you already, just edit that. And your program has to print exactly hello, space world, I am ready for CSCI 26, and then a new line. That's what my auto grader is going to be looking for. So yeah, I'll do some of that in just a second. I do just want to walk you through the idea of like editing a file and compiling it if you've never learned the terminal yet. We teach it here at Clovis, so I'm sorry if you haven't learned it before. I'm going to assume knowledge of it. Do read that Learning the Shell guide on our Canvas optional reading page. If you have never touched the terminal before, that will help you a little bit. And then of course come to office hours, come to the tutorial center. We will get you up to speed one way or another. But if I want to do something on the terminal, if I want to edit a file, I have to use an editor, and so I like to use Vim in this class, and I'll use that later. But I want to teach you an easier editor called Nano right now. So if I have a file that I want to edit, like hello.cpp, that's a file that I'd like to open up and change and save after I've made some changes, I'll say the name of the editor, Nano, followed by the name of the file, hello.cpp, and if I hit enter, that plops me in to the Nano editor. Alright, and so I can use the arrow keys to move around, and you see some helpful commands at the bottom. It's saying the character stands for the control key. So if I type Control G right now, it will tell me some help about the Nano editor. If I type Control X, it will ask me, do I want to save? And then it will exit Nano. So it's Control X for save and quit. So that's how that all works. And then of course I can start typing and like move around and backspace. It's like Microsoft Word, essentially. Alright, so let me make a version of this hello program that's slightly correct, but mostly correct, but slightly incorrect. How about that? And you'll have to fix it. Alright, so I'm giving you most of the first program. Very easy, right? Just making sure we understand how to get a program made, compiled, and run. So, stream using namespace standard int main. And then I'll do return 0, and then cout hello world. I'll forget all the extra stuff about CSCI 26, and I'm ready for it. So there is a program. I've changed this file, and I'd like to quit out and save it and go back to the terminal to compile and run it. So I can do Control X for exit. That will ask me, do I want to save? Y for yes. And it'll say, what file do you want to call this? I just want it to be the file that I'm editing right now. I want it to be overwritten. So I'll hit enter. It's already filled out for me. And then it changes the file, and hello.cpp is still there, but it's the new version now. And I can come back to it if I want. Go back into Nano. You see that my changes are still there. Control X to exit again. So that's all there. And to compile a program and run it, so you go to the file, wherever it is. So I'm in the same directory where hello.cpp is. I want to compile it. And then if it's just one file, we use the g++ command to, that's our compiler. So I give it the name of the file that I want to compile. Then if I want it to be called something other than a.out, I say -o, give the name of the executable file, usually without any extension, whatever I want it to use to run it. So I want to compile hello.cpp, I'll say g++, hello.cpp, and I want the executable file to be called just hello. That's a standard convention. So I'll hit enter, and if there were no errors, it will be happy to compile that into a final file. So there it is. There's my hello file that it generated from hello.cpp. It compiled it, and to run it, you say / name of that executable file, / hello, and then when I hit enter, it will run that program that we just compiled. So there it is, hello world. It's almost correct. I've forgotten a few things. The autograder is going to yell at me when I show that to you later. So that's pretty much your hello world program. That's pretty much the setup for working in Nano. I do encourage you to learn Vim when you have time, all right, if you don't know it yet. So that's the first program that you are going to be working on. There are, of course, many more files here, so let's talk about the rest. So for the next part, I want you to make a program that determines whether a number is prime. All right. In the primes.h file, in the header file, you're going to be you'll see the isPrime function that you will implement in primes.cpp. All right. You can pretend that you're always given a number greater than or equal to 2. So you have to like say, it's the age-old question, like is 1 prime or is it not? You don't have to care. Oh, sorry, not hello.h, it's prime.h that I want to go and look at. So here is the one header file. It's declaring one function is prime, and this is the function you will be implementing in the corresponding CBP file. So you're going to return true if the number that you were given is prime, and false otherwise. So you're going to have to test, was the number I was given as my argument, was it prime or not? So right now it's definitely wrong, so you're going to fix this. Okay? So is prime, given a number, pretend that that number is positive, greater than or equal to 2. All right? There are a few ways to test for primality. Your book has some pseudocode in section 9.4 that you can implement. I have an example in Racket. I'll show that to you of how to test for primality. Test if a number is prime. Let's see. Oh, sorry, I copied the wrong thing anyway. Dun dun dun. So let me fix that. Lab 0 0. Dun dun dun. There. Now it's happy. And so if I go inside this lab 00 folder, I pre-made some code in Racket. Primes.racket. And here is how you make a function that tests for primality. Here's one way. What does it mean to be prime, right? It means that no numbers other than 1 in itself divide into you. So like the number 27 is not prime, 25 is not prime, but 29 is prime. Or just like 5. 5 is prime, right? Why? It's because no number between 2 and 4 goes into 5. That's because all the numbers don't divide into 5. That's what it means to be prime. The only divisors of 5 are 5 and 1. All right? So, to check for primality then, what you should do is you should iterate. You should iterate between 2 and your number minus 1. Try to divide your number by those numbers. Try to divide 29 by 2, 3, 4, all the way to 28, and see if any of them go in. right? See if that number, so I'm looping from I between 2 and n minus 1. See if I divides cleanly into n. If it ever does, if there's no remainder, you can use the modulus function. You can use %sign in C++. If there's no remainder, excuse me, that means your number was not prime because it went into that number cleanly. This number that would be a factor of it. So like set a little helper variable like guess that it's really prime, but if you see that there's a number that goes into it, then it wasn't prime, sadly. Okay, so do a loop like that. That's kind of what your textbook has as well. And then your final result was that variable. Like did you ever find a factor? If you did, that will tell you that it wasn't prime. If you never found a factor, it will stay, yes, it was prime. Okay, so that's the idea. Let me run it in Racket. And so %sign or number sign f means false, and then t means true. So 25 is not prime because it got to 5. Like I got to 5, and if you divide 25 by 5, you'll notice that there's nothing left over. The remainder was 0, so that means 5 is a factor of this number. Oh no, that means it's not prime. Same for this one, once it gets to 3 or 9, right? Or 6, maybe, I'm not sure. No, 3 or 9 go into 27, and it'll stop. It'll notice the 3 first, right? When I is 3, it'll try to divide 27 by 3. Oh, that goes in 9 times with nothing left over. There's no remainder, so it was not prime. But then 29, you try all the numbers between 2 and 28, try to divide, see if there's anything left over. There's always something left over. There's always a remainder because it's not clean. It's not going in cleanly. It's not a factor. There are no factors. It's prime. Right? So that's how you notice if a number is prime or not. Technically, you're just looking for one factor, so you can go between 2 and the square root of the number if you really wanted to, but this is probably easier to do it for the first time. So yeah, that's primality. Your book does have some helper code for you that looks a bit more like C++ if you'd like to look at that, but this is pretty much what I want you to implement in C++. Okay, so yeah, definitely making this first lab very easy for you. So that's primality stuff. Get that working, and you're going to then compile and run that program. So here is, we got, primes.h, primes.cpp, and testprimes.cpp. Those are all a bunch of files coming together, all right? I've made a make file to make this much easier for us, but for example, you'll just say make test primes, and it will like compile all the correct stuff. It'll work out just fine. So, but looking at the files individually, primes.h, that holds the declaration of that is prime function, primes.cpp, you're going to implement this body, give it the right thing, and then the file with the main function that checks if you're doing it right is this testprimes.cpp file. All right. So here I have a bunch of tests checking for things that are prime and things that aren't prime. So here's a bunch of prime numbers, here's a bunch of not prime numbers, and your function should be able to get it right both times. So right now it's saying that everything's prime, but to compile and run this, you say make test primes using the make file. And then if it doesn't complain, you saw that it did a bunch of stuff, it made some files, and it made this final file that's executable. Test primes, and so it's running all these tests. Obviously, it's right half the time given all my tests, but you want it to be right all the time. So yes, all these things are prime because the function is saying everything's prime right now. So it's getting all these wrong down here. So that's the prime file. Get all that working. And then I would say that the most complicated example, but the most fun example is the last one. It's where you calculate pi to decent precision, not great precision, but decent precision. So there's a way to calculate pi by throwing darts. It's really cool. So let's look at those files. So here is pi.h, pi.cpp, and then testpi.cpp. That's the main file with the tests. So pi.h has a few things. It has a class that I've implemented for you called point. We'll get into that, but I've pretty much implemented this class for you. You're just going to use it. This is the function that you'll be using, approximate pi. You're going to use the point class to get at that. So I've made some functions here, but you can think of a point as like a two-dimensional thing. It's holding an x and a y coordinate. So every point object is holding some coordinate in 2D space, and you're going to use that in this approximate pi function. So here's like the implementation of the point class. There it all is. And I've given that to you. But your job is to implement approximate pi. So given a certain number of virtual darts, you are going to throw them against a virtual dart board, and in a certain way, that will calculate pi. So I have to explain the setup for you, but once I explain it, it should make a lot of sense. But this is the function that you'll be implementing, approximate pi here, using the point class. All right, so here's the setup. You're going to throw num darts virtually at a dartboard. All right, so there's going to be a hint of randomness in here. You're going to randomly throw num darts onto a square with a circle inside of it. So there's your dartboard, but the square is like framing that circular dartboard. All right, and pretend that it's centered at the coordinates 0, 0. So this is where the points come into play. So when you throw darts, dun, 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 imagine this is your dartboard. Again, you have a 2x2 square, and here's a circle of radius 1. So like here's your circle, here's its center. It's got radius 1. This is 0, 0, by the way. And it's got radius 1. And then obviously this is a 2x2 square that's surrounding it, because like the diameter is 2. It's just hugging it ever so slightly. And let's pretend you put a blindfold on, and you are throwing darts, and your darts, they always land within the square. It's guaranteed. They always, like, it's magnetic somehow, but they're not guaranteed to land within the circle. So sometimes you're going to throw a bunch of darts, right? Num darts many, and sometimes it hits inside of this circle, and sometimes it hits outside the circle. If you can only throw things within the square, like if you're throwing random darts, right? Sometimes your darts are going to land within the circle, sometimes your darts are going to land outside that circle, okay? And surprisingly, this is all you need to calculate pi. Because if this is truly random, all right, truly random, you put on a blindfold, you're throwing at random. Again, a lot of darts are going to land inside the circle, but some are going to miss and just land in the corners, in the white places. The darts, they were random. They approximate, right? What's the probability that it's going to land within the circle versus outside the circle? It has to do with the area of the circle, right? Because if it's random, it's going to hit proportional to the area of that circle. And the area of that circle has pi inside of it, doesn't it? So that is going to lead to an answer. So the dart's approximate area, and the ratio of the area of the circle, right, to the area of the square is what? 1 is the area of that circle. It's pi r squared, pi 1 squared, right? Pi times 1, if I can draw pi properly. There we go. Pi 1 squared, that's just pi. So the area of this circle, unit circle, is pi. And then, what's the area of the square that's surrounding it? It's 2 times 2, right? So that's 4. And so the ratio of the area of the circle to the area of the enclosing square is pi over 4. And because you're throwing darts at random, it just so happens, and I hope you can kind of see this, that the number of darts that land within the circle divided by the number of darts that you threw approximate pi over 4. Does that make sense? That's the idea. So that's what you're going to count. All right? Just count how many darts land within the circle versus land outside the circle. And that gives you pi over 4. Multiply that answer by 4, and you get an approximation for pi. Isn't that great? So that's beautiful. So that's what you're going to be doing. You're throwing num darts at a random dartboard using this function, uniform random point. Now that's throwing your dart for you. And that ratio will calculate pi over 4. Remember to use double division rather than integer division. And then multiply the answer by 4, and you have an answer for pi. You have an approximation of pi that's not great, but it's going to be like 3.14-ish. Close enough, which is really fun. So we are going to make some simplifying assumptions. First of all, how do you know? Like, we're going to throw darts by generating random points. First of all, let me show that to you. Let's see. So we're going to call a uniform random point. That's doing its thing of generating a random point. And so let's say you get this point over here. Am I still in green mode? Yeah. So let's say you throw your dart and you get this point. How do you know that this point is within the circle versus this point over here is outside the circle? What you do is you calculate its distance to the origin. So that point there, what's the distance from here to here? You know it was within the circle if that distance was less than or equal to 1, right? Because that's the radius. So that's how you know where you were. Like here I was within the circle. I was outside the circle because the distance from the center to this dot is greater than 1. Cannot be within the circle. Does that make sense? That's how that's working. So that's pretty much what you're going to be doing. You're going to be calculating the distance from origin of that uniform random point that you just generated. Right? So you're just going to be calling these functions that I've already implemented for you, but that's why you're using that. Okay? Just check if that distance is 1. Okay? So we are going to cheat though. If you look closely at my uniform random point, my point generation function, it is randomly making points, but it is going to return to you a point that always has positive or 0 coordinates. So we're actually going to only be working in the upper right. That's the first quadrant. So that's going to work out just fine as long as, because the ratio is the same. I hope you see that. Like we're actually secretly going to be working between here and here. Like here's -1, -1. Here's 1, 1. So we're really going to be doing our work within the first quadrant. And the ratios are all the same. You don't have to worry about anything because it's a quarter of this big thing. So really our points will only ever land like here or like out here. They're never going to go down here because that's not what's being randomly generated. But you can use the same formula, so it's the same. You just multiply this, like, think of it 4 times. It's all symmetric, so it's all fine. So that's our optimization. We're only going to throw darts in the first quadrant, but the formula, everything we talked about, still holds. You unfortunately have to throw a lot of darts for this to get close to pi, but that's fine. We don't care. This is a computer. It can do things fast. So yeah, that's pretty much it. What you're going to be doing is you're going to be calling a static method to generate a point. All right, so I need to show that to you. Let's open up also pi.h because that's where the declaration of all this stuff is. You'll notice, you may have never seen this before, go back to your CSCI 40 textbook. Points uniform random point method is a static method. So it does not, and it actually creates a point for you. It gives you back a point. You do not need a point object to run this method. It belongs to the class. That's what static means. It belongs to the class, so you can use it just by itself. Right? So a static method belongs to the class itself rather than to an object, so you can't use a dot to call it. Instead, you say class name : that static method. It's kind of like a function that belongs to the method. That's how that works. So you say class name : static method. That's how you're going to call it. So to generate a random point, to throw a random dart, which we will be doing in a loop a bunch of times, here's how you do it. Here's how you run this uniform random point function and get back a point. You're going to say, you call it like this. You say point : uniform random point. That's a weird way to call it. And that just immediately gives you back a new point. You can put that into a variable, point p equals that. And that was you throwing a random dart. All right, now you gotta ask it for its distance. This is a normal method, so you gotta say p dot distance from origin, because now you have a point to work with and real member variables. But that is how you're gonna use those two functions, and that's all you need from the point class to throw a random dart. All right, and then you're gonna have to check, like, was it inside or outside? Keep that count, and then the number of darts you threw, you already have that, because that was your parameter, and create that ratio and give back an answer, and that's pretty much your pi program. So let's look at the test pi.cpp file. This is the one with the test. It's just let's see. It'll run your code so you can actually see it work, and then I also have a bunch of tests. The auto grader is going to be checking for these tests, though. So I'm going to run your code on throwing a million darts to approximate pi. I'm going to do that 10 times. Then I'm going to make sure that it's pretty close. It's like within 0.1 of the actual value of pi. And it will be if you do it right. So yeah, and that's your test pi.cbp. Again, you'll compile and run in the same way as the other one. You'll say use the makefile. You'll say make test pi. And right now it's saying that 42 is pi, so it's going to get it wrong. But you can run it, test pi. And so I've failed all my tests because that's what my random value of pi is, negative 42 right now. Not good enough. So got to fix that. But hopefully you understand what to do for that now. And that's going to be the last part of your lab. So once you're done, you're happy with your results, you can turn in your lab as much as you want before the due date, by the way. Just keep track of when that due date is. It's listed on Canvas. But you're ready to submit your code whenever you're ready. You want to see partial credit or you're finally done. You want to turn everything in. You're going to use this turn in command on the class server that I've made for you. So you're going to say turn in, name of the lab, @, it's like an email, @ name of the class, lab00 at CSCI26, and then you're going to space separate all of the files you'd like to turn in. These are the 3 files you'll be turning in by the end. All right. So I've really only implemented hello.cbp, so I can just run this part of the command. But your final turn in is your grade, so make sure to run this at the very last time. All right. That's the idea. But you can keep on submitting until the end of the due date window, or the end of the semester if you missed that window. All right. But so it's not like the first turn in is your grade. It's the last turn in is your grade up to the due date. Okay. So you run this, and that's going to run the auto grader. So you're immediately going to get some feedback, which is great. So I will say turn in lab00 at CSCI26, and then I'll space separate all the files I want to turn in. I might as well just get you used to turning them all in right now, but there's no use to turn in the rest. So hello.cbp. Every other file I'm using the default version of, so don't touch any other files that you're not turning in. This list are the only files you're allowed to touch, because those are the ones you're turning in. Hello.cbp, primes.cbp, pi.cbp, and then I hit enter. And hopefully, if there's no issues, yell at me if it says something's not working right, but this submits your assignment. It starts grading it. You can sit and watch if you'd like. You can close this submission with Control-C if you don't want to, but it'll grade it pretty quickly, unless it's like the due date and it's grading everybody's. And then it's going to upload your grade to the class website to be viewed in a nice clean way. So at the end, it's like, I'm finally done with everything. Control-C to close this program and get back to the terminal. So I'll type Control-C right now. And there's 2 ways to look at your grade. I prefer it if you use the class website, so I'll show you that way first. All right. So log in as yourself on the class website, lottensclass.com. Remember that this is a similar account to your class server account, but it's a different one. Same username though. And I hope that that's the password. But right now the password is the same as your username if you didn't change it. These are 2 separate accounts. Cool. So you're going to scroll down to lab grades. Click that to look at the grade for your lab. Hit it. And it will tell you in a nice, very color-coded way why you got 6.5 out of 27. All right, so you're just going to keep turning this in until you get full credit. But do you see how nice it is? It's going to color-code like why you got the Hello World program wrong. It's like, this was your output on the left. This is what it was supposed to be. The minus is like, get rid of this and then add this, and it'll be correct. So this is trying to tell you what's going wrong. And so you can hopefully see that and be like, oh, okay, I understand what to fix now. And then the rest is like, okay, some of these pass, some of these don't, because half the numbers were prime. So you get a little bit of credit there. And then pi, we got no credit because that was not a good value of pi, that default value that I put there. You have to fix that. So this is your grade. You can see it that way. And you just keep on resubmitting until the due date, and that final grade is your grade. All right. So that's that. There's also a terminal-based way, if you just want to look at it quickly. It's not as color-coded and beautiful, but you can say view-grades. And it'll give you an option for like, which values for your grades do you want to look at? I've turned in a few things for a bunch of different classes, but you'll just have option 0. That's your most recent one. You say option 0, I want to look at this grade, lab 00 at CSCI26. Hit enter. And then you can scroll up with the arrow keys and scroll down with the arrow keys. You can also use the Vim keys, but here's like a text-based version of your answer. So trying to be helpful, but it's not as color coded. So I encourage you to use the website instead. But that's another way to look at your grade. And then Q to quit out and go back to your terminal. So that's how you look at your grade after you turn it in. That static method, that's turning in your lab. So yeah, if you don't want to do your work on the class server, you sure don't have to. You just got to get these files back somewhere because the turn-in command is on the class server. All right, so that's the name of the game right there. But yeah, turn it in up as many times as you need to, up to the due date. But you can run these tests on your own end. So really, in theory, you should only have to turn in once you get it all working, or you want partial credit. So that's Lab 0. So please let me know if you have any questions about that. Yell at me on Discord, and I will see you next time.